Okay, I'm going to change totally the direction of what I was talking about now to go back almost to the previous presentation. I'm going to talk about emulating instruments or other equipment in real time and doing that emulation very fast. So basically, if you want to, say, emulate a camera with a SpaceWire interface, we think we can probably do that within a day instead of several months of programming. Okay, so what I'm going to do is show you how we basically do this. And the problem we had is that STAR-Dundee would sell something like PCI or compact PCI or whatever interface boards, and then people would use these to do instrument emulation as part of their integration and testing and development activities. And then they really run up against this problem of, okay, we now need to write this real-time software to work with this board to provide a certain level of performance. And while our drivers are very efficient, sometimes we couldn't actually meet their requirements, and that was an issue. So we thought about this and came up with a different way of doing it, which is what I'd like to talk about now. Okay, so the SpaceWire EGSE, or Electronic Ground Support Equipment, as we call it, so maybe think about it as an emulator. It's some SpaceWire test and development equipment that we developed at STAR-Dundee, and its aim is to rapidly emulate instruments or other SpaceWire equipment in real time. And by real time, we mean to within a microsecond. Okay, so it's better than you could ever do with any real-time software. And the aim is for integration and test purposes. So we basically generate user-defined packets in a predefined sequence at specific times and data rates. I'll explain all this in a minute. So an example is we're maybe developing a mass memory, and in order to develop that mass memory, we need to have an emulation of the camera so we can get that data stream coming into the mass memory. Another possibility may be you're developing software for your control computer, and you need sort of emulations of all the instruments that are attached to this. So these have to be real time, so you can actually test that your software works in real time on the complete spacecraft system. Okay, so we replace that camera with our SpaceWire emulator, which is simulating the camera. Okay, so how does it work? So what we do is we define the instrument behavior in a script. We then use some software to effectively compile this script and load it into our EGSE unit. And then hardware functions, not a processor, but some hardware functions, actually run this script independent of the host software, which gives it its real-time performance. So the benefits are that we can drastically reduce the time and cost associated with traditional instrument or equipment emulation, and all the real-time behavior is handled by hardware, so you literally don't have to worry about that. Okay, so the hardware itself is shown here. This is a little box. It's one of the boxes about this sort of size. It has two SpaceWire interfaces, some triggers. It includes 128 megabytes of memory inside. We've got some logic analyzer connectors, and there's a USB connector for connecting up to the host computer. This shows the front panel, so there's the two SpaceWire interfaces and various LEDs and triggers. And on the back, we've got the USB interface, power. We've got some logic analyzer connectors for helping debug things, and some more triggers as well. Okay, so the software that goes with this includes the compiler, which compiles the scripts into our configuration files, and then a loader which basically loads these configuration files down into the hardware. Then we have a software API so that when you're running your emulation, you can actually talk to your software, because your software may be interested in doing other emulations, like you might have a MIL standard 1553 emulation that you want to run at the same time as the SpaceWire one, and you need these two to communicate. So we can handle that sort of communication as well. And then there's a graphical user interface, which basically just helps with the putting all these bits together. So this actually shows the graphical user interface. There's an editor here for the language. Up the top, we've got some software events you'll see later, and notifications which are coming up from the EGSE, and you can do things like start, stop, and so on. But, okay, so the scripting language is very versatile. It's very easy to use, and it's very SpaceWire specific. So we have packet definitions, because we want to send and receive packets. We've got variables so we can define packets with dynamic data. We have a packet schedule, so it tells us when exactly we want to send packets. We've got a state machine to emulate instrument behavior, so we can take in various events, and the state machine will respond to those events and control the particular packet generation schedule that's going to take place. Okay, so here's our first simple script. So at the top, we basically set the speed of the SpaceWire links. Okay, so this is the base signaling speed, 200 megabits per second these are set to. And then we define a packet. So this is packet number 1, and it contains 4 decimal bytes followed by an end of packet marker. So, and even I can understand this software. Okay, and then we have a schedule. This is named schedule number 1. That basically says send packet number 1 after 500 milliseconds, and send it at a real data rate of 100 megabits per second. So even though the link's set to 200 megabits per second, our instrument can only send 100 megabits per second, and we want to be able to emulate that as well. Okay, so we can tell it what real data rate to use. And then we have a state machine, and the state machine here simply says just send schedule number 1 repeatedly. Okay, so what we're going to expect from this is we'll see a packet, then we'll wait 500 milliseconds, and then we'll send that packet again repeatedly. So if we look at our link analyzer output, and just to explain, okay, this is the data being sent in one direction and time goes down the way. This is the information being sent in the other direction. Okay, so what we're interested in is this column here. And okay, so first of all, down the bottom here, we can see that the links are set to 200 megabits per second. And you can see that between these packets, we've got 500 milliseconds gap. Those packets are, I should say, the yellow is the first character of a packet. The blue is the next characters, and then the sort of, I don't know what sort of colour that is, the pinky purpley colour, whatever, is the end of packet marker. So you can see we're sending 1, 2, 3, 4, which is defined end of packet marker, and each of them has a 500 millisecond gap between. Okay, so if you wanted an instrument to do that, then in 5 minutes you've created that instrument, running that in real time. Okay, but you can do things much more advanced than that. So we can do things like have declare variables. So we've declared a random variable, which is an 8-bit random variable. We've declared here a constant variable with the value 2, and we've got an incrementing variable with starting off with value 0, and then we've got a CRC variable as well. And then we can use these variables in the packet. So this packet's name packet number 1, it's got a constant header, it's got an incrementing ID, and then it's got 8 random bytes, and then it's got a CRC calculation. And we can start where the CRC calculation starts taking place, and then when we stop the CRC, we can then add in the CRC value at an appropriate location. So we can specify the coverage of the CRC code. And then we've got the end of packet marker. Oops. Then we've got a schedule that just sends this again. If we look at that, then this is the result. So we've got our constant header, which was number 2. So that if you look at all 3 packets, you can see the number 2 appearing there. Then we've got an incrementing ID. So it's 1 on that one, it's 2 on the next one. Sorry, it's 0 up there, it's 1, then it's 2. Then we've got the random bytes. Okay, and then the CRC value, which is calculated and inserted in there. Okay, so the next example basically allows us to send 3 packets. So we've got packet 1, 2, and 3, and each has got some unique data. So this time we're defining them in hex, so it's all 1s, all 2s, all 3s. And then we have a schedule that basically is a little bit more advanced. This time we've got 3 schedules we're defining. The first one just waits 1 second and then sends packet number 1 5 times. The next schedule waits 500 milliseconds, then sends packet number 1. Waits, then 1,000 milliseconds after the start of that schedule, it will send packet number 2. And then 1,500 milliseconds after the start of that schedule, it will send packet number 3. And finally, schedule 3, we send packet number 3 immediately, and then 1 second later, we send packet 2, and then 1 second later, we send packet number 1. Okay, so we can define in various ways when we're actually going to send the packets in the schedule. Okay, that's what I've just said. Okay, so then we set up our state machine, which is now going to, it now has 3 states. So we're in state 1. We execute schedule 1 once, then we transition to state 2, and it's an unconditional transition. Then in state 2, we execute schedule 2 once and then transition to state 3. And finally in state 3, we execute schedule 3 once and then transition to state 1. Okay, and here we can actually see the results of that. So we've got schedule 1 with the appropriate timings, schedule 2, and then schedule 3. Okay, so you can see we've got various packets that we can define. We can also do things like, if you wanted to, say, simulate a camera, you might actually have some real data that you want to send. We've got 128 megabytes of memory on the device, so you can actually load, say, 100 images, 1K by 1K images, into that memory, and then you can actually send those. So we have mechanisms for actually downloading information from files, and that file information can then be sent as well. So if you wanted to simulate a camera, which was just squirting out images at a predetermined rate, you can actually do this probably in about an hour at the most, I would say. It would take you to do that sort of real-time simulation. Okay, so you can actually download real information, you can generate information randomly, you can combine these, you can have fixed data or whatever, and then you've got the scheduling. For the state machines, we've also got events. Okay, so and this allows you to build up complex behavior of your emulation. Okay, so here we're looking at software events. So we've got a software event named software event 0. And the software event is something that comes down from the host software into our EGSE system. So it could be that you want our instrument, the camera, to be turned on by a mil standard 1553 interface. So your software has got a mil standard 1553 interface. It receives a certain command, it checks that command, and then it sends a software event down to us, and we then start doing the real-time SpaceWire execution. So that's the idea behind these software events. So we've got, we basically change the state whenever software event 0 is detected in this case. So we've got the 3 states sending the 3 different schedules, and then every time we have software event 0, we move from one state to the next. Okay, so those events that are moving from one state to another, they can be things like, well, the software events. They can be external triggers. So we have 4 triggers that can be bidirectional triggers. So you can actually have up to 4 triggers, hardware triggers going in, and use those to trigger events. We've also got some pattern matchers. So, because one of the things you might want to do is, say, have your camera, and because it's got a SpaceWire interface, you're going to use something like SpaceWire RMAP to control this camera. So you're going to send an RMAP command to the camera to turn it on. So what we have is a pattern matcher. When a SpaceWire packet comes in over the link, it will do a pattern match on that. if that pattern matches, then it's going to trigger an event, and you can use that event then to trigger or to change state and then change the schedule that's being sent in that state and so on. There are a number of these pattern matches. I think it may be something like 16 pattern matches for each of the two interfaces in this EGSE unit. You can also trigger on time codes. So one of the protocols we're currently working on with the European Space Agency is called SpaceWire D, which is a deterministic data delivery version of SpaceWire, which uses time codes to trigger sending information over SpaceWire links. And so we can emulate this with this, this system as well. Okay, so just to follow that example through, so you've got your camera, it receives the camera emulation, it receives a command to say switch it on. That command goes in, it gets matched, that matching causes a trigger, that trigger causes you to change state, and in the next state you're then starting to send out images repeatedly every 100 milliseconds or whatever it may be. And then maybe you receive another software command and another RMAP command to maybe switch you off. And then maybe you receive some hardware trigger, which is some error condition or whatever. So you can change the states according to actually the different events that are actually occurring. Okay, so one of the things we did is at a SpaceWire working group meeting, it was probably last year, around about this time, we showed a demonstration of this, and we challenged the audience. I'm not going to do this today, but we challenged the audience then to say, give us an instrument and we'll simulate it, and we'll bring it to you and show you it working tomorrow morning. Okay, so I had one of my engineers with me, and he was a bit nervous at this, as you can imagine. Fortunately, somebody came along and said, okay, and he had 3 instruments he wanted simulating, which was maybe a bit unfair. But we said, okay, we'll do 2 of them. The reason we couldn't do the 3rd is we wanted to do, ideally we'd have done all 3 at the same time, but it needed a router so we could actually merge the information from these 3. So we said we'd do 2 because the EGSE unit has 2 SpaceWire interfaces. And the SpaceWire working group meeting went on, finished a bit late, and then there was a dinner, and there was plenty of wine at the dinner, and we didn't finish till about 11, and so my poor engineer, he then went back to the hotel, got all the kit out, and started coding up. It took him around about 2 hours, so he did get some sleep that night, and the following day he had these 2 instruments simulated and up and running, and this was actually for Meteosat 3rd generation, but he got those 2 instruments simulated, and the guy that we did it for was very happy at that. So, we decided that we would then simulate something a little bit more involved. So I had an MSc student from a university in Sweden, Luleå University in Sweden. He came over for 6 months and wanted to do a fairly ambitious project. So we said, okay, simulate Solar Orbiter. Solar Orbiter's an ESA mission, which is currently being developed. It's very similar to the Bepi-Colombo mission. So his project then was to use our EGSE system to simulate Solar Orbiter, and he had to also develop some other emulations as well. What we were interested in is understanding what the capabilities were and what the limitations were, because we wanted to know how we could improve it. Okay, so we selected the Solar Orbiter because it was a new ESA mission, so the equipment, the simulations might be useful for this. It has a routed SpaceWire network. It uses CCSDS packets, the packet utilization standards, and importantly, most of the documentation was available because it was based on Bepi-Colombo. Normally, you can't get information about current spacecraft designs from ESA, but because it was based on Bepi-Colombo, there was actually quite a lot of information available. This just shows the spacecraft itself and the various instruments on board the spacecraft. So the key thing is this actually shows the architecture. So there's all of the instruments and then there's 10 of them, and then each of they basically feed into a number of routers, SpaceWire routers. They then go into this memory unit. So there's an input module, then the memory array itself, an output module, another SpaceWire router, and then it goes out to the transfer frame generator for sending down to ground. There's a supervisor and processor module which basically controls the operation of everything, including the memory. This is all cross-strapped to a redundant set of equipment which looks identical. Okay, so this is a schematic diagram of the same thing. So here we've got various instruments are down here. These feed into these routers, then into this mass memory array, and then out up to the telemetry system. And over here, there's a router with the supervisory module, which is controlling the router itself. So this was the demonstration network. We agreed to give this student 4 of the EGSE units, several routers, and various other equipment. And he then had to use this and built in the simulation PC, which is at the top, he built a simulation of the onboard computer and the mass memory. And then he was using the EGSEs to simulate all the instruments. This actually shows the equipment actually running. So the EGSEs are on the top, the routers are on the bottom, and the white boxes are our USB bricks. So he had that running fairly well. So just to summarize this, so we've got this new concept for SpaceWire instrument emulation in real time. The aim was to minimize the development time. So we think a day or 2 for most instrument real-time emulation. If it's a complex instrument with lots of state changes, then maybe it will take a bit longer. But it's of that sort of order. It's a number of days, not number of months. We can integrate with other test equipment via the external triggers. We can interact with the host software, sending software events from the host to the EGSE or from the EGSE unit to the host. And receive SpaceWire packets can also be passed up to the host software. So if you want to do some, depending on the data contained in a SpaceWire packet, which you can't do with the one of our pattern matchers, then you can actually send that packet up to the host computer, and it can then determine whether you should actually change the state of the unit. So that equipment's all running fine. We've done this real-time emulation of the solar orbiter. The student did a fantastic job and actually got the whole thing up and running, which was very good. And he identified some limitations. Mainly, he would have liked some more states. We have, I think it's 32 states, and each state can have up to 5 or 6 inputs. Okay, so for some of the solar orbiter instruments, we could have done with some more states to handle all of the error conditions. And that's something we're actually looking at putting in. So the results of that are now being used to basically improve the capabilities of this unit. Okay, that's me. So if there's any questions, I'll be happy to answer them. I don't know where the microphone is.
Michael Phillips of Lucky. So in the initial integration of like the camera or some other instrument with it, seems useful initially just to get the ICD packet information flowing out over there. Do you have the capability to collect real data from the vendor, right, with the link analyzer, and then play that back, dealing with jitter and missing packets and things like that, right? So for more realistic emulation. Yeah, because it seems like you had the file playback. I'm just wondering whether those files seem to be in a scripted format or something like that. Is there a possibility to collect snippets of real data from early EDU testing from the vendor and incorporate it into the model?
Right, okay, so not with this unit. So this unit's intended to emulate the instrument basically as specified. So before the instrument's been developed. But we're currently just finishing the design of what we call a SpaceWire recorder, which has that sort of capability. So the idea with the recorder is that we have you want to understand what's going on across the complete spacecraft. So you basically, each of the SpaceWire links you feed into our recorder system, and then it will actually record the data, and then you can basically analyze this and potentially play that back if you need to.
Other questions? Yes.
So it looked like a lot of the work here would be applicable outside of SpaceWire and the space domain for just generic network protocols. Did you think about that, or did you look at existing tools for simulating or standing up protocols quickly in other domains?
So our focus was entirely on solving this problem for real-time simulation of emulation of SpaceWire instruments. That was really what we were focused on.
Other questions? Nope. Okay, thank you.
Okay, thanks very much.
So I would like to remind